Okay, so this is first in a series of a few videos dealing with electrochemical cells. And so in this video I'm going to try to fairly briefly explain the components of what is known as a galvanic cell. Now, galvanic cells you've seen before, you may not realize it, but batteries, rechargeable and non-rechargeable batteries, car batteries, all those types of batteries are actually simple galvanic cells. Well, they're not getting more complicated, but they're galvanic cells. So galvanic cells, one of the first incarnations of a galvanic cell is this battery. It's called the Voltaic pile. It was developed by Alessandro Volta, an Italian chemist, around 1800. All he did was stack interchanging discs of copper and zinc, and in between them he had these little pads that had been soaked in sodium chloride, so they were electrolytic. They could allow transfer, and so it was the spontaneous discharge of electrons as a result of a redox reaction that allowed for the generation of this current. Volta didn't realize that at the time, but that's really what it was. It was a redox reaction. And so as you can see, galvanic cells are a little more sophisticated now than they were 220 years ago. But anyways, let's sort of look at a generalized galvanic cell and see what the components are. So we're going to talk about this cell, a Daniell cell. A Daniell cell is copper and zinc. So copper is solid, zinc solid, and it also has solutions of copper and zinc, and we'll see about those in a minute. And essentially, we can look at this Daniell cell as two different half cells. And so here's a beaker containing a solid, so I'm going to label that as zinc solid. And so in my solution here, I'm going to have zinc sulfate. And so really what I'm interested in is the fact that that's zinc 2 plus and sulfate SO4 2 minus, because it is aqueous. So they're dissolved in solution. All right, so that's one half cell, and so I can write an equation for that. We're going to have to determine what equation it is, but we'll see that in a minute. I have another half cell here, and so this is the copper solid, and so in solution what I have is copper 2 sulfate. And so again, of interest there, copper ions and some more sulfate. So sulfate is actually a spectator ion, but it's still there in solution. It does play a role to some degree. Okay, now these are two electrodes. So in a battery you see a positive and a negative terminal labeled, and so we have to label these two half cells as positive and negative. So let's just quickly determine how we're going to do that. These two electrodes are known as the anode and the cathode. So how do we determine the anode and the cathode? Well, we have to consult this table. It's known as a standard reduction potential table. So these are all half reactions are all written as reductions, and they are associated, each reduction half reaction has associated potential as compared to 0 for a hydrogen half cell. And so basically what this means is anything with a positive cell potential compared to hydrogen means whatever is positive gets reduced, and hydrogen would be oxidized. By the same token, anything with a negative cell potential will be oxidized and hydrogen would be reduced. That's kind of how the table works, and we're going to talk about this in a bit more detail a little later. But so just knowing our way around, so anything high is likely to be reduced, anything below it is going to be oxidized. Okay, so let's find our two half reactions. So here's our copper half reaction, and here's our zinc half reaction. Okay, and so you notice copper is above zinc on this table, so that means copper is reduced, and that means zinc is oxidized. Okay, and so we can use that information to label our half cells, and here's a really good reminder of which is which. Red cat, reduction occurs at the cathode, and so our cathode is going to be copper because copper is reduced. That means zinc, which is oxidized, is our anode. Okay, so red cat, reduction occurs at the cathode. Copper has a higher standard cell potential, so it will be reduced, so it will be the cathode. So let's go back to our Daniell cell. So now we can label these as our anode and our cathode. So zinc is our anode. It is going to be oxidized. Copper is our cathode. It is going to be reduced. Just a couple other things we want to label here. This is our conducting wire. We have to conduct those free electrons from the zinc. Remember, the zinc is getting oxidized. It's losing electrons, so electrons are going to move through that conducting wire. And this is known as a salt bridge, and I'll talk a bit about more about that in a minute. Okay, so that's initially there's our setup for our Daniell cell. The anode is a zinc 2 plus half cell. The cathode is copper 2 copper half cell. We have a conducting wire that allows for electron transfer between the two metal electrodes, and we have a salt bridge that also has to be present in this electrochemical cell for the cell to work. Okay, so now I'd like to talk about moving to electrons and ions. Let's look at the first one, the movement of electrons first, because it's a little more straightforward, and we've kind of already dealt with that. So here are two half reactions at the anode and the cathode. If you remember, zinc is oxidized, so this is now written as an oxidation half reaction. Electrons are lost. They're the electrons that are lost. So these electrons essentially are lost at this electrode as zinc solid is oxidized. And so they can then move through this conducting wire. And so they end up moving to the copper cathode, the copper solid cathode. And so at the cathode, reduction occurs, but it's copper 2 ions in solution that are reduced. So copper 2 plus electrons yields copper solid. So here's the direction of electron flow. And it's always the same direction of electron flow, anode to cathode, because at the anode oxidation takes place, providing the electrons. At the cathode, reduction takes place, using those electrons. So the electrons have to get from the anode to the cathode. So that's the direction of electron flow. Now the other thing we have to look at is ion movement, because here's the thing: if we did not have this salt bridge here, we would get no current, no electron flow, because we would very quickly get polarization, or a very rapid buildup of negative charge. And once you have that rapid buildup of negative charge, electrons will not flow. So we have to overcome that. And so I mentioned the salt bridge. This salt bridge contains any aqueous solution, and you want it, it's typically better if it's not reactive, so it's not necessarily a component of the system. So potassium nitrate is a very common one, because, as I'm sure you remember, nitrate is very soluble, potassium is very soluble as well. So we have potassium nitrate in our salt bridge. And so here's what happens. As the electrons are produced, as the oxidation is proceeding, we get increased zinc 2 plus in solution. Every zinc atom that is oxidized becomes a zinc ion in solution. So we rapidly get increased zinc 2 plus. And so what happens? This nitrate is capable or able to move into the anode. And so the NO3 minus moves to the anode. And so that anode stays essentially electrically neutral. The zinc 2 plus is increasing, but you're also moving in these anions into the anode. So anions to anode is a good thing to remember to maintain electrical neutrality. Well, what's happening on the other side? Well, on the other side, we're getting in our cathode, we're getting a decrease in copper 2 concentration as copper 2 ions are oxidized. And so in this case, K plus moves in to the cathode. And it moves into the cathode again to match that decrease in copper 2 plus charge. So positive charges are being used in the reduction process, so K plus positive ions move into the cathode to maintain that electrical neutrality. And so again, cations to the cathode. And so that basically occurs with any galvanic cell like this. You need ions in solution, or these ions that can move either to the anode or the cathode to maintain electrical neutrality and maintain that electron flow or that current that you're trying to establish. Now, the last thing I do want to mention in terms of labeling cells is a sign, and you've seen this on batteries, positive and negative. And so the anode is given a negative designation. And so it may seem a little counterintuitive that anions move towards a negatively charged electrode, but it's not really negatively charged, it's just a designated charge. Really what the anions are moving into is a response to increase in cation concentration. That said, the cathode must be positively charged, and again, cations moving into a positively charged electrode, well again, it's not that. Cations are moving in as a consequence of a decrease in the concentration of positive charges within the half cell. So it may look counterintuitive, negative charge moving to a negative electrode, but it's not really counterintuitive. It's that they're moving in response to a change in concentration of a different ion. So that's all I'm going to talk about at the moment with galvanic cells. That's a brief introduction of the components and electron flow and ion flow within these half cells. And we'll talk more about electrochemical potentials, cell potentials in a subsequent video. So for the time being, that concludes this video.